Hello and welcome to the following revision session on the particle model of matter for GCSE Physics in the Combined Science course. So, the particle model was proposed by John Dalton in 1819, and Dalton proposed that all substances were made from indivisible spheres which he called particles, and Dalton proposed that all solids had the same formation of particles, all liquids had the same formation of particles, and all gases had the same formation of particles, which he called the particle model of matter. So Dalton proposed that solids had the following formation, liquids had the following formation, and gases had this formation. Now this particle model of matter has many limitations associated with it. It doesn't show the forces between the particles. Particles are not actually solid spheres of the same size. Particles are always in motion and not stationary, but we can use the particle model of matter to explain many phenomena in the natural world, such as density. Now density is a measure of how much mass there is in a certain volume. So it's the number of particles in a certain volume, or it is the measure of the space between the particles in a certain volume, or it is a measure of how spread out the particles are in a certain volume. So if an object is very dense, it has lots of particles per unit volume, so therefore there are small gaps on average between the particles in the substance. If an object is not very dense, there are large gaps on average between the particles in the substance. There are few particles per unit volume. So density is the mass of a substance in a unit volume, and we can calculate this with the following equation. Density is equal to mass over volume, where mass is in kilograms, volume is in meters cubed, so density is in kilograms per meters cubed. Now you are expected to memorize this equation for your examination, and you should be able to rearrange it. So density is the mass of 1 cubic meter of a substance. Now we can symbolize density with the equation rho is equal to m over v. Now the unit of density can be written as either kg/m cubed or kg m to the minus 3. Now just note the unit of density can always be written as the unit of the mass you've used in your calculation divided by the unit of volume that you've used in your calculation. So the units of density depend on the units of mass and volume. So as we said before, we've got this idea of a dense object and of a not very dense object. So this tells us that solids have a high density and gases have a low density. So solids, there is not much space between the particles per unit volume, but there is in a gas. So in a gas the particles are more spread out per unit volume, in solids they are not very spread out per unit volume. Now technically a vacuum has a density of 0 kilogram per meters cubed, as there are no particles in the volume at all on average. Now to work out density, what we say is we write the equation density equals mass over volume, we place the values into the equation, and we write our answer with the correct significant figures and the correct units. Now if the shape is symmetrical or regular, we can find its volume by using one of the equations you use in mathematics. So volume of a sphere is equal to 4 over 3 times by pi times by r cubed, where r is the radius of the object, a volume of a cube which is equal to L cubed, where L is the length of an object, and the volume of a cylinder, okay, which is given by pi times by r squared times by h, where r is the radius of the object and h is the height of the object. Now we can then calculate the value of density by using the previous equation, where using density equals mass over volume, which you can work out your volume with the mathematical equation. So for example, if it was a sphere, you do 4 over 3 times by pi r cubed and then pop that into the equation. Now you can carry this out in a practical investigation as well. So you would need a top pan balance, a ruler and some materials. So you would take a material and place it on a balance, ensure the balance was zeroed beforehand, and you measure the mass of the material. Then using a ruler you measure the 3 different lengths of the material, calculate the volume and then calculate the density. So you get a balance and ensure the balance is zero. So if the balance reads a non-zero value when there's nothing on it, it has a zero error, which is a type of systematic error. So to remove a zero error, you either subtract the value from the reading or reset the balance. You would then get a 30 centimeter ruler that can measure to 1 centimeter, so therefore it has a resolution of 1 centimeter. The resolution is the smallest possible value that can be read on a device. So a high resolution gives an accurate result. You would then get your symmetrical object, okay, and then you would place the block on the tray and record its mass, remembering to ensure the balance reads 0 before the mass is placed on it, and then using a ruler you would measure the different lengths of the dimensions of the block and then use that to calculate the volume. Now there is a better way to measure the length of a small object rather than using a ruler as your measuring device. To increase the resolution of the volume measurement, you should use a more sensitive device than a 30 centimeter ruler, which we could use as a screw gauge gauge micrometer which has a resolution of 0.01 millimeters. So increasing our sensitivity of our device increases the resolution, giving more accurate results. And it's the same also for a vernier caliper, another measuring device you can use to calculate the length of a particular dimension. Now always ensure as well that you align your ruler so the scale is starting on the edge of the material as shown on here, okay, and then you can use that to calculate the volume of the material and then the density of the object. Now we can also do this to find the density of different irregularly shaped objects by using a top pan balance, a 400ml beaker, a 100ml measuring cylinder and some materials. So you would take an empty 400ml beaker, fill it with 200 centimeters cubed of water, which is the volume before in the experiment. You then gently place a piece of material in the water and record the new volume in the beaker. That's the volume after in the experiment. You then subtract the volume before from the volume after to find the volume of the material. You then remove the material from the beaker and place on the electronic balance to find the mass of the material. You can then use this to calculate the density by saying density is mass over volume, and do this for different materials. So you get a balance and ensure the balance is zeroed. If the balance reads a non-zero value and there's something on it, it has a zero error. So a zero error is an example of a systematic error, which is an error of the same value in each measurement. So to remove your zero error, like we said before, you either subtract your value from the reading or reset the balance. Now remember, you always record your results to the resolution of the balance used. So you get your 400ml beaker and then you fill it up with 200 milliliters of water from the tap. Always ensure it looks straight on, otherwise you may get a parallax error, which is an example of a random error, as in each measurement the error is a different value. Now you can reduce a random error in science by taking repeats and averaging the value. You retrieve your material of your non-symmetrical materials table. You then place the material on the balance to measure its mass. Okay, you then place the material in the 400ml beaker of water. This will cause the water level of the water to rise in the beaker. Then you measure the new volume of the water with the materials in it. You can then work out the volume of the material by doing final volume minus starting volume. Then you can work out the density by doing mass over volume. Now in the particle model, we should consider all forms of energy stored in the particle structure, and there are two forms of energy stores present in the particles, which are atoms or molecules, and that is the potential energy store, which is due to the intermolecular forces of attraction between the particles, and the kinetic energy store due to the particles moving. So we refer to these two stores of energy together as the internal energy of the substance. So the internal energy of the substance equals the kinetic energy store plus the potential energy store, but this is of all of the particles. So the particles within a system have a kinetic energy store, which is due to their movement. The particles are also a potential energy store due to their intermolecular forces of attraction. The sum of all of these particles' kinetic and potential energies represents the body's internal energy, which is the kinetic energy of all the particles plus the potential energy. So all objects in our universe are made from particles. So the energy these particles have in total is the internal energy of the substance. Now the part of the internal energy is the kinetic energy, which is how much the particle vibrates, which can be changed by changing the temperature of the substance. Increasing the temperature increases the kinetic energy store. So that this can be achieved by doing work into a system by heating it up. Now another part of the internal energy store is the potential energy of the particles, which is how much the particles are attracted to each other. Now this can be changed by changing the state of the object. So the potential energy can be increased by changing a substance from a solid to a liquid to a gas. Now this is a very important idea because this can also be achieved by heating up, by doing work into the object. So our internal energy equals the kinetic energy plus the potential energy of all of the particles. Now the internal energy of the system can be changed if a change is made to the particle system of an object. The kinetic energy can be changed if the temperature is changed, and the potential energy store can be changed if the state of matter is changed. However, only one store can be changed at once. They can't be altered simultaneously. Now a heating curve shows the change in temperature of a substance when energy is placed into the substance. So when the temperature changes, the kinetic energy store changes, which is an upwards line on the graph. But when the state changes, the potential energy store of the system changes, which doesn't affect the kinetic energy store, so it doesn't affect the temperature of the system. So you can see this on a heating curve as it is a flat line, because the energy is going into changing the potential energy store, not the kinetic energy store. So this energy which has been put into the substance to change its state is hidden from the temperature observation, so we call it a latent energy or a latent heat. Now, latent means hidden, so latent heat is hidden heat, as is the energy hidden from the thermometer. Now, the specific latent heat is the energy needed to change the state per kilogram of the substance. Now, the latent heat needed to melt a substance is smaller than the latent heat needed to boil a substance. You can tell this from the graph, as the line is longer for boiling compared to melting. Now, this occurs because there's a greater change in the forces of attraction going from a liquid to a gas as compared to a solid to a liquid. Now, remember, we can identify the state change from a heating curve. It's a flat line. So at that point, it's a change in the potential energy store. We can identify a change in temperature because the line is moving upwards, so it's a change in the kinetic energy store. So either you've got a change of temperature or a change of state, or you've got a change in kinetic store or a change in potential store. Now, just remember that what's going on is when an object is heated, the potential energy will, the internal energy will increase, which is either an increase in the potential energy or is an increase in the kinetic energy of the substance. Now, the physics of heating and cooling is identical, just that heat requires work to be done into the internal energy store of the system, whilst cooling requires work to be taken out of the internal energy store of the system. So in this example, the internal energy is decreasing with time as energy has been taken out of the system. Now, we can also look at substances when they change between their states. Now, when substances change between their states, the internal energy is changed in the substance. It either increases or it decreases. An example of this is ice melting into water, of water boiling into steam, of water freezing into ice, or of dry ice subliming from solid to gas. Now, this state of matter is referred to as a physical change because the material will recover its original properties if the change is reversed. But like a chemical reaction, in a physical change, the overall mass of a substance is conserved. So if you have 20 kilograms of a solid, it will turn into 20 kilograms of a liquid, which will turn to 20 kilograms of a gas. So we need to know the different names of the state changes between the different states of matter. So if we've got our solids, liquids and gases, a solid going into a liquid is called melting, which requires an increase in internal energy as the substance is being heated for this to occur. So it occurs at melting point. A liquid turned into a solid is called freezing, which is a decrease in internal energy as the substance has to be cooled for freezing to occur, but that also occurs at the melting point. A liquid turned into a gas is called boiling, which requires an increase in internal energy as the substance has to be heated to achieve this, which this occurs at the boiling point. Now, a gas turned into a liquid is called condensing, which is a decrease in internal energy. So we know this because the substance is cooled for condensing to take place, but that also occurs at the boiling point. Now, a solid turning into a gas is known as sublimation, which requires an increase in internal energy because we know that the substance is heated for this to occur. Now, a gas turned into a solid is called deposition. Now, this works because there's a decrease in internal energy because the substance is cooled. Now, previously we have said the internal energy is equal to the kinetic energy of all the particles plus the potential energy. The kinetic energy due to the movement, the potential energy due to the attraction. Now, we can never calculate the total internal energy of a substance easily, but we can calculate the change in the internal energy of a substance. Now, the change in the kinetic energy store can be looked at with the specific heat capacity. The change in the potential energy store can be looked at with the specific latent heat of the substance. Now, we can always work out the change in the kinetic energy store or the change in potential energy store with different equations. Then you can add the values together to work out the total change in the internal energy of the substance. So, to understand this, we need to know that the specific heat capacity is the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius, whilst the specific latent heat is the energy needed to change the state of 1 kilogram with no temperature change. So, we know the change of temperature occurs when our line and our heating curve is going upwards, but our change of state is occurring when that line is flat. So it's either a change in kinetic energy store or a change in potential energy store. It's either governed by the specific heat capacity or the specific latent heat. So we can work out the change in kinetic energy by doing the equation E equals m times by c times by delta T, where m is the mass in kilograms, c is specific heat capacity in joules per kilogram degree Celsius, and delta T is the change in temperature in degrees Celsius. Whilst the change in the potential energy store is equal to mass times by latent heat in joules per kilogram, m times by L. So the equation on the left refers to the energy transferred into or out of a substance when it changes temperature. The equation on the right works out the energy transferred into or out of a substance when it changes state. Now these equations are given to you in your examination, but for higher tier examinations it'll be likely you'll be asked to rearrange these equations. Now as we said before, we can identify the state change or the change of temperature from a heating curve. Now remember, the energy per kilogram needed to change from a state from a solid to a liquid is called the specific latent heat of fusion. The energy per kilogram needed to change the state from a liquid to a gas is called the specific latent heat of vaporization, and we know that the specific latent heat of vaporization is always larger than the specific latent heat of fusion for a substance, because there's a greater change in the forces of attraction going from a liquid to a gas than a solid to a liquid. Now to answer these questions that involve these equations, the important thing to do is step 1 is to write out the equation, number 2 check your units and then place the values into the equation. You then calculate an answer, then put a unit on your answer and write it to the correct number of significant figures. Now again, if you have a change in temperature, remember you've got to work out the change in temperature first before you input it into an equation, and then finally it also works the same for the latent heat equation. So you write out your equation, you place the values into the equation after you've checked your units, you then calculate an answer, place a unit on the answer and write this answer to the correct number of significant figures. Now the last thing we want to look at is gases. Now to understand gas pressure, you've got to understand how gas particles operate on the particle model of matter, because we say gases can freely move, they move randomly in all directions, and they have a variety of speeds. Now gas particles are freely moving, so have a high kinetic energy store, but they're very far apart from each other, so have low forces of attraction, so a low potential energy store. So a gas's internal energy is made up mostly of the kinetic energy and very little potential energy. So the molecules of a gas are in constant random motion, and the molecules of gas move in random straight line directions with a variety of speeds. Now there are 3 properties of a gas which can be measured: the volume, the temperature and the pressure. Now let's consider these properties by considering a gas particle in a box. Now when we consider placing gas particles in a box, we say it's in a closed system because the gas particles cannot escape. Now gases follow different laws in open and closed systems, but in this course we're only going to consider gases which are trapped in a space in a closed system. Now the volume of a gas is the space occupied by the particles that make up the gas, and it is the volume of the gas that, so the volume of the gas is the space between the particles. It's the space the gas can fill. It's not the volume of the gas particles themselves. The volume of a gas is much larger than the volume of the gas particles that make it up, as shown in the following diagram. Now temperature is a measure of the average kinetic energy of the particle. It's the average speed of the particle. So temperature is linked to the speed of the gas particles, and temperature is related to the average kinetic energy of the particles in a gas. So the higher the temperature, the faster the gas particles move on average. The lower the temperature, the slower the gas particles move on average. Now remember, kinetic energy and speed are an average because gas motion is random. Now work can be done on a gas, which means we put energy into the gas. This can be done by pumping up a gas in an enclosed volume or blowing up a balloon. Now if we do work onto a gas, we'll put energy into the gas, and if energy is given to the gas particles, it means the internal energy of the gas is increasing. Now as most of the internal energy is kinetic energy, this means the temperature of the gas increases. Now pressure is when a gas particle collides with the walls of its box, and it does so, it exerts a pressure on the box. Now this pressure is always exerted outwards as the particle is colliding with the inside of the container. Now it's better to say that when the particle collides, it exerts a force on the side of the container, which acts at right angles to the container. Now the force exerted by a gas is always outwards from the container it is in. Now truly, the reason why a force is produced is because when the gas particle collides with the container, it's changing its momentum when it does so. So gases have the following properties. Property 1, the temperature. It's a measure of how fast the gas particles move, and it's related to the average kinetic energy of the gas particles. Property 2, the volume, a measure of the space which the gas particles can fill. And property 3, pressure, pressure, a measure of the force exerted at right angles to the container when the gas particles collide with that container. Now we can consider the particle model when we keep our volume of our gas constant. Now this means the box that the gas is in has a fixed size, and we can use the particle model to find the relationship between the temperature of a gas and the pressure exerted by a gas. Increasing the temperature of a gas increases the average speed of the particles in the gas. So if the gas particles are moving faster, they will produce more collisions. More collisions increases the pressure of a gas. Now remember, a high pressure can cause the container to explode or break. Now if we slow the molecule down, we lower its temperature, the molecule will hit the sides less often. So moving slower gives less collisions. So it gives a lower pressure exerted by the gas. This tells us that as temperature increases, pressure increases. The relationship is in direct proportion. Now, that's only one reason why we see this relationship for the gas, because if we increase the speed as well as the particle collide with the sides more often, it will hit the side with a greater force. So moving faster gives collisions with a greater force, and more forceful collisions give a greater pressure, and this high pressure can cause the container to explode or break. Now moving slower gives collisions with a smaller force. Now less forceful collisions give a lower pressure. So like we mentioned before, as the temperature increases, the pressure increases. The two are in direct proportion to each other, and there are two reasons as to why this occurs. Now if we look at experimental results, we can see that when we plot pressure against temperature, we get a straight line through the origin, as that indicates a direct proportional relationship between the two. So in a closed system, a gas follows the following laws. When the volume is kept constant, the temperature and pressure are directly proportional. Increasing the temperature increases the pressure, as there are more collisions and more forceful collisions per second. So what should we know in this course? That density is equal to mass over volume, and you should be able to use the particle model to explain the different states of matter and the differences in density. You should be able to recognize and draw simple diagrams to model the differences between solids, liquids and gases and understand their differences in density. You should be able to use appropriate apparatus to make and record measurements to determine the densities of regular and irregular solid objects and liquids. Now volumes can be determined from dimensions of regularly shaped objects and by the displacement technique for irregularly shaped objects. Now dimensions can be measured by using apparatus such as a ruler, a micrometer or a vernier caliper. Now it's also important to note that energy is stored inside a system by the particles that make up the system, which we call the internal energy. So it's the total kinetic energy and potential energy of all the particles that make up the system. Heating changes the energy stored within the system by increasing the energy of the particles that make up the system, which will either raise the temperature of the system or produce a change in state. Now you should be able to describe how, when a substance changes state, either melts, freezes, boils, condenses or sublimates, mass is conserved. And changes of state are physical changes which differ from chemical changes because the material recovers its original properties if the change is reversed. Now if the temperature of a system increases, the increase in temperature depends on the mass of the substance heated, the type of material and the energy input into the system, which you can symbolize with the equation E is equal to mass times by specific heat capacity times by a change in temperature, where the specific heat capacity of a substance is the amount of the energy required to raise the temperature of 1 kilogram of one substance by 1 degree Celsius. Now the specific latent heat of a substance is the amount of energy required to change the state of 1 kilogram of the substance with no change of temperature. So E equals mL. Now we can have a latent heat of fusion, a change of state from solid to liquid, or a latent heat of vaporization, a change of state from a liquid to a vapor. Now the molecules of a gas are in constant random motion. The temperature of the gas is related to the average kinetic energy of the molecules, and changing the temperature of a gas held at a constant volume changes the pressure exerted by the gas. And you should be able to explain how the motion of the molecules in a gas is related to its temperature and its pressure, and explain the relationship between the temperature of a gas and its pressure at a constant volume. So I hope you've enjoyed today's revision session where we've looked at the particle model of matter in GCSE Combined Science. Thank you very much for listening and have a lovely day.